Equilibrium constant, quantifying equilibrium. Looking at activity, activity is how we're going to define our plugged in value into the equilibrium expression. Activity is the contribution of my component of a mixture to the system as a whole. So for a solid or liquid that's a pure solid or liquid, we define activity to be 1 for pure solids and liquids because pure solids and liquids don't have concentrations. They are not mixtures of anything, they're simply pure solids and liquids. Their value becomes incorporated into the value of the equilibrium constant, and so we will not even write a solid or liquid in our equilibrium expression if it is a pure solid or liquid. A solution has an activity of its molarity against 1 molar, and a gas has an activity of its partial pressure in a mixture, or its pressure if it is a gas by itself, against 1 atmosphere. So the pressure of the gas against 1 atmosphere. This has the effect of making the Kc constant unitless. Any particular set of values that I plug into my equilibrium expression should always produce the same value for Kc, but I can have almost an infinite number of different potential values that I can plug into my equilibrium expression and produce the same Kc value. For example, 1/2 and 2/4 and 4/8 and 8/16 are all the same in terms of the ultimate value they produce, which is 1/2, 1/2. These different set of values that can go into the equilibrium expression are called equilibrium positions. And the equilibrium position for the same temperature has a constant K value. This essentially infinite number of values for different sets of data give us our various different what we call equilibrium positions. If I look at this particular equation here, it has 2 different sets of data in 2 different trials where we have activities of SO3, SO2, and O2 for trial A at 0.056, 0.344, and 0.172 respectively, and for B 0.076, 0.424, and 0.212 respectively. If I plug these into the expected equilibrium expression, which would be the SO3 squared divided by the product of the SO2 squared times the O2, we're going to get 0.15 for both sets of data. These are 2 different equilibrium positions, but they produce the same value for the equilibrium constant. Now I can figure out an equilibrium constant from equilibrium concentrations fairly easily. If I know that I have some particular concentrations that are for my system at equilibrium, given a reaction like this, the Haber process of ammonia forming from the combination of nitrogen and hydrogen, we can calculate the Kc value in a 5-liter container if it holds 3.01 moles of nitrogen, 2.10 moles of hydrogen, and 0.565 moles of ammonia at equilibrium. Our first step is to convert each of these numbers of moles into a molarity by dividing by the volume. So the molarity of the N2 becomes 0.602, the molarity of the H2, 0.420, and the molarity of the ammonia, 0.113. We can then plug these different molarities into my formula for converting to activity, and since they're all molarities, we're going to divide them all by 1 molar, producing activities that are numerically the same value but lack units. These activities can then be plugged into the equilibrium expression of ammonia raised to the 2nd power divided by the product of nitrogen and hydrogen raised to the 3rd power. And if I plug these in, I can plug in 0.113 squared divided by 0.602 times 0.420 to the 3rd, and the final result I should get is a Kc value of 0.286. For the reaction of antimony pentachloride producing antimony trichloride and chlorine, I can determine equilibrium concentrations from a Kc just like I can determine the Kc from equilibrium concentrations. It's a bit more lengthy process, but it can be done. If I have a Kc value at 448 degrees Celsius of 2.51 times 10 to the negative 2, if I take 10 grams of antimony pentachloride in a 5-liter container at this temperature and it comes to equilibrium, I want to know how many grams of antimony pentachloride will be present in the equilibrium mixture. The first thing I need to do is calculate the molarity of the antimony pentachloride. The molar mass of antimony pentachloride is 299.02 grams per mole. So I take the number of grams that I have and multiply by the molar mass to find moles at 0.03334 moles. I take that number of moles then and divide by 5 liters, and I get 0.006668, which comes out to be 0.00667 molar. Given the molarity of 0.00667 molar, if I convert that to an activity of 0.00667, I can take my equation of antimony pentachloride producing antimony trichloride and chlorine, and I can set up what we call an ICE table. If I take initial concentration of 0.00667 activity for the antimony pentachloride, and since no antimony trichloride or chlorine were mentioned, initial activities of 0 respectively for each, a change in concentration of some value that we do not know, negative x for antimony pentachloride because it loses some value, positive x for both antimony trichloride and chlorine, and both being just x, not 2x or 3x, simply x because the ratio is 1 to 1 to 1 stoichiometrically, so negative x, and positive x. At equilibrium, we expect to have concentrations of 0.00667 minus x for the antimony pentachloride, x for the antimony trichloride, and x for the chlorine. If my Kc is 2.51 times 10 to the negative 2, I can plug this into my equilibrium expression, and plugging in the values, I wind up with 2.51 times 10 to the negative 2 being equal to x times x divided by 0.00667 minus x. I can simplify this by combining the x on top to x squared, and then if I multiply both sides of the equation by the denominator 0.00667 minus x, I'll get 1.67 times 10 to the negative 4 minus 2.51 times 10 to the negative 2x being equal to x squared. If I move all of my numbers over to the right hand side of the equation, I'll have 0 equals x squared plus 2.51 times 10 to the negative 2x minus 1.67 times 10 to the negative 4. This becomes now a quadratic equation, and as you can probably guess, we can solve for the value of x using our quadratic formula. So the quadratic formula, if you don't remember from mathematics and algebra, is that the value of x is equal to the opposite of what we call b plus or minus the square root of b squared minus 4 AC over 2a. In this particular equation, the value of a is the constant in front of the x squared, so 1. The value of b is the constant in front of the x, so 2.51 times 10 to the negative 2. And c is the final number, negative 1.67 times 10 to the negative 4. I can take these three values, I can plug them into my quadratic equation, and I get negative 2.51 times 10 to the negative 2 plus or minus the square root of 2.51 times 10 to the negative 2 squared minus 4 times 1 times negative 1.67 times 10 to the negative 4 divided by 2 times 1. Simplifying this, I get negative 2.51 times 10 to the negative 2 plus or minus 0.03603 divided by 2. When I work this out, I get two possible values for the system. I can get a value of negative 0.0306 or a value of 0.00546. I am going to select the positive value because I cannot have a negative change in my numbers of moles. I cannot have negative moles, rather. And so I'm going to use the 0.00546. If I plug this into my initial concentration of antimony pentachloride at equilibrium, which was 0.00667 minus x, plugging in x, I get 0.00667 minus 0.00546, giving me 0.00121 molar. If I multiply my molarity of 0.00121 molar by 5 liters, I'll get 0.00603 moles. Multiplying that by the molar mass of 299.92 grams per mole gives me a value of 1.80 grams of antimony pentachloride at equilibrium from the 10 grams that I began with. Now, for some of these kinds of systems, it is possible to simplify using approximations. If Kc is a very small value, then I know that my reactant is going to be dominant in my equilibrium. A large initial concentration in a reactant-dominant situation means that I'm not going to lose very much reactant overall. So the change in reactant is going to be negligible there. If I have a system of A producing 2B reversibly, with a Kc of 3.3 times 10 to the negative 5. If I assume that at my initial beginning of my reaction, my concentration of A is 1 molar and there is no B, then I have a concentration of A of 1 molar and a concentration of B of 0 molar. Plugging in an ICE table for this, my initial activity is 1 for A, 0 for B. I will lose X as my change for A. Now notice, because the equation was producing 2B, I have 2x there. My stoichiometric ratio was 1 to 2. So at equilibrium, I have 1 minus x for A and 2x for B. If I plug this into the equilibrium expression for this system, I expect to get 3.3 times 10 to the negative 5 being equal to 2x squared over 1 minus x. Simplifying this then, I get 3.3 times 10 to the negative 5 equals 4x squared over 1. I do this because I'm going to assume that the x value in the denominator is negligible. After simplifying this equation then, I wind up with 3.3 times 10 to the negative 5 equals 4x squared. If I divide both sides by 4, I'll get x squared being equal to 3.3 times 10 to the negative 5 over 4. Taking the square root of both sides gives me an x value equal to the square root of 0.0000825, and that value comes out to 0.00287. If I do this by the approximation, I get an x value of 0.00287. If I take this same process and work it through the quadratic equation, I will also get 0.00287. I can compare my value of my approximation to my starting concentration so that I compare x to my initial concentration of A, and in doing so, 0.00287 divided by 1 can be converted to a percentage. The ratio of x to A is going to give me a percentage value of 0.287%. So my amount of x that I lost was 0.287% of the amount of A that I began with. If my approximation has an x value that is less than or equal to 5% of my starting concentration, I'll assume that it is a negligible change and that the assumption that I can ignore it in the denominator is valid.